Hello and welcome to the next series of short talks, this time about potential and current dividers. Part 1, the potential divider. Right. You will notice that the title of this slide is in title case, with all capital letters and an exclamation mark. This is unique amongst all of the slides in this module. I have chosen this title because this is, without a doubt, the most important circuit in the entire module. We will be coming back to this one again and again in a lot of different varieties and situations. Understanding how this circuit works and being able to quickly analyse it is going to be very useful for understanding the rest of the module. So, what is a potential divider and what does it do? Well, it is a series of two resistors connected together like this. There is a potential, in this case about 5 volts, put into the top of the potential divider here. The bottom of the potential divider, in this case, is connected to ground, 0 volts. And because the current is flowing down through these two resistors and losing some potential as it goes, the potential where the two resistors meet, the voltage at this point, will be somewhere between the top of the potential divider at 5 volts and the bottom of the potential divider at 0 volts. Exactly where it is between the top potential, 5 volts, and the bottom potential, 0 volts, depends on the ratio of these two resistors. In this case, 3.33 and so on volts. Being able to work out this output voltage, given the input voltage and the values of the two resistors, is a very useful skill, which we will use and come across in a whole variety of different situations as we go through the module. So, how do you do it? Well, let's first of all start thinking about what's going on in this circuit. Here, I've built up the circuit in the simulator, and we can see that there's going to be a current flowing down through these resistors. Using the control-click trick, I can print up what these currents are, 1.67 milliamps in this case. There is no current flowing through the voltmeters because these are ideal voltmeters and they have an infinite resistance, so no current flows through them. That means by Kirchhoff's current law, all of the current flowing down through this resistor must carry on and flow down through this resistor. So the currents flowing through these two resistors are the same. And that gives us the clue as to how we can work out what the output of this circuit is going to be. Let's have a look at this on a bit of paper. Okay. So, we've got 5 volts at this point here. This goes through a resistor, in this case 1K, and that goes through another resistor, 2K, down to ground. There are various different ways to analyse this circuit and come up with the answer, but probably the easiest way is to consider that you've got two resistors here in series. Now, two resistors in series behave like the sum of the two resistors. So in terms of the current flowing down through this series of resistors, it works exactly the same as this. A single resistor with a value of the sum of the two resistors. We can now work out what this current must be. We've got 5 volts across this 3K resistor. We know the resistance, 3K, so a simple application of Ohm's law, voltage across the resistor is the current through the resistor times the value of the resistance. The voltage across the resistor, 5 minus 0, is just 5. The current through the resistor, we don't know. The resistance is 3K. So the current must be 5 divided by 3K, which is 1.667, or about 1.67 milliamps, as the simulator has worked out already. Right, if we know the current flowing down through these two resistors, then we can work out the voltages across these two resistors. Just consider the 2K resistance for now. Apply Ohm's law to the 2K resistor, and what we would get is the voltage across the 2K resistor is the current through the 2K resistor times the value of the resistance. Delta V equals the current flowing through it, 1.67 milliamps, times the resistance, 2K, equals divided by 1,000, because it's milliamps, multiplied by 2,000, 2K, 3.34 volts. If I was working this out a little bit more accurately, and actually wrote that as that, then I would get the exact value that the voltmeter is showing in the simulation, 3.333 volts. That is the difference in the voltages across this 2K resistor. So this delta V here is this voltage here, I'll call it V out, minus ground. So in other words, V out minus 0. That's delta V for the 2K resistor. The voltage on one side minus the voltage on the other is 3.33 volts. Therefore, the output voltage must be 3.333 volts. And we have solved the potential divider equation for this circuit. Fine. But we don't want to go through this type of derivation every time we have a potential divider to work out. We'd like to find a formula that we can just input the voltage at the top of the potential divider chain and the values of the two resistors, and it would tell us what the output voltage is. And we can work out that formula quite easily, and it's a formula that's worth learning because it comes up so often. So, let's have a look at how to do that. In general then, we'll have a voltage. I'll call it V in. This will go through a resistor here, which I will call R1, down through another resistor, which I will call R2, down to, in this case, ground. And what I want is, what is the output voltage there? V out. Right. Well, first of all, the current. The current that's flowing down through there is the current that you'd get from a voltage V in across a resistor of value R1 plus R2. Because these two resistors are in series, so they behave like a simple resistor with the sum of R1 and R2 as its value. So applying Ohm's law to V in and the sum of these two resistors gives me that the current flowing down here is V in over R1 plus R2. Strictly speaking, I possibly should have written V in minus 0, because the voltage across these two resistors is the voltage here minus the voltage there. But instead of writing V in minus 0, I've just written V in. It's the same thing. Once I've got the current, I can work out what the voltage across R2 is going to be. The voltage across R2 will be the current, which is in this case V in over R1 plus R2, multiplied by the value of R2. It's just Ohm's law again. Delta V equals I times R. That's my current. Right, but VR2 is Vout minus 0, the voltage across this resistor R2. So if VR2 is Vout minus 0, then VR2 must be equal to Vout. So I could just write Vout, the output voltage of my potential divider here, is Vin times R2 over R1 plus R2. And that is it. The potential divider equation. Worth learning. We can check that it works by substituting in the values for this potential divider that we've got up here. Vin is 5 volts, R2 is 2K, R1 plus R2 is 1K plus 2K, which is 3K. So the answer would be 2/3 of 5, which is 10 over 3, which is 3.33 and so on volts. But that is the key important formula that it's really useful to just know. There's a slight variation on this formula, which we use in some other circuits. And that's just what is the ratio of Vout to Vin. We get that formula just by dividing both sides of this formula by Vin, and that simply gives us Vout over Vin equals R2 over R1 plus R2. And that's the second formula on the slide here. Okay, that's it. That's the basis of potential dividers. Next time, we'll have a quick look at current dividers.